We're getting so close, really close, to building a single universal AI that can learn to see and understand our world, pretty much like we do. And today, we're diving into a massive leap forward in that quest. It's a new foundation model from Meta AI, and it's called DINO 3. But how do you even start to teach a machine to see? It's the huge fundamental question, right? Imagine if you didn't have to. What if an AI could just learn to see by looking? Just by observing the world, the same way a kid does, without anyone telling it, that's a dog or that's a tree.
Okay, so to really get why DINOv3 is such a game changer, you gotta understand the two main ways we've tried to tackle this whole computer vision thing up until now. All right, on one hand, you've got the old school way, supervised learning. Just think of it like this. It's a student with a teacher who is constantly pointing at things. This is a cat. This is a car. This is a stop sign. It means humans, actual people, have to sit there and label millions upon millions of images. Then there's the other path, self-supervised learning, or SSL. And this is totally different. The AI is basically on its own. It's like a student just wandering through a library, figuring out patterns and connections all by itself, with no labels, no teacher.
And that first method, the one with the teacher, it has a massive, massive problem. We call it the annotation bottleneck. Can you imagine the sheer amount of human effort it takes to label billions of images? It's not sustainable. It simply doesn't scale. And that's where self-supervised learning really shines. This is the promise, right? The idea that we can finally break through that bottleneck. How? By letting the AI learn from all the raw, messy, unlabeled data the world has to offer. Think about it. Once you don't need labels, you can just unleash these models on the internet. You can tap into this basically infinite ocean of images out there. We're talking about a scale of data that for computer vision was just a pipe dream until now. And when I say scale, I mean, wow. The DINOv3 team put together a dataset of almost 1.7 billion images. And get this, that was curated from an initial pool of 17 billion. That is just a mind-boggling amount of visual information. But that's exactly what you need if you want to create an AI that has a really general, robust understanding of the world.
So the strategy they took? It's pretty much ripped straight from the large language model playbook, like with GPT. The idea is simple. If you scale up the data and you scale up the model itself, you start to see these incredible new abilities emerge. So that's what they did. They scaled DINOv3 all the way up to 7 billion parameters. But as it turns out, it wasn't quite that simple. Because when they pushed things to this incredible new scale, they ran into a wall. A really strange, hidden problem where just making the model bigger didn't automatically make it better at everything. They hit this thing they call dense feature degradation. It's a bit of a mouthful, but here's what it means. As this giant model kept training, something really weird started to happen. It was getting smarter at big picture stuff, like telling you, yep, that's a cat. But at the same time, it was getting dumber at the little things, the fine-grained details. It was losing its ability to see the texture of the cat's fur, for example. So this created a huge dilemma. You can see it right here. For those big, global tasks, performance just kept climbing. Awesome. But for the dense tasks, the ones that need you to understand every single pixel, performance started to dip. It was actually getting worse the longer it trained. A total paradox. So that's the puzzle, right? How do you fix that? How do you build an AI that can see the whole forest without going blind to the individual trees? That was the challenge they had to solve. And their solution is actually super clever. It's a technique called gram anchoring. The best way to think about it is it's like forcing the model to stop and look back at its old notes. Specifically, its notes from early on in its training, back when it was really good at seeing all those tiny details. It uses that cleaner, earlier version of itself as a kind of guide, a North Star, to make sure its current understanding of the world doesn't get all fuzzy and blurred. Okay, so they solved the big problem. Now for the fun part. What can this thing actually do? Well, the results are pretty amazing. This is where it all comes together to create something like a universal eye for pretty much any visual task you can throw at it. The result is, honestly, incredible. We're talking about a single, frozen foundation model. Now, frozen is key here. It means you don't have to retrain it for every little task. You can just take this one model right off the shelf and it smashes state-of-the-art results across a whole bunch of different jobs. It's a huge deal.
And look, the numbers don't lie. This thing works. On these really tough, detail-heavy tasks, DINOv3 doesn't just inch past what came before, it completely blows it out of the water. Just look at the score for semantic segmentation. That is a massive jump. That's its ability to understand what's in every single pixel. And then for monocular depth, where lower is better, you can see it just crushes the old error rate. These aren't small improvements. These are huge leaps. So what does that mean in practice? Well, it means it has this whole suite of superpowers. It's amazing at those dense tasks like segmentation. It just gets 3D space in a way that's kind of spooky. It's so consistent that you can use it to track objects in a video. And maybe coolest of all, it can look at a picture and just find the objects in it, all on its own. No labels needed.
Let me give you a concrete example of just how precise this thing is. Imagine you point to one tiny little detail in a picture, say a single cross on the front of a huge building. The model instantly lights up every other identical cross across the entire photo. That's what having those clean, super detailed features gets you. It's incredible. So where do we go from here? What does this all mean for the future of AI? Well, the really cool thing is, this isn't just about one huge monolithic model. It's about creating a whole new toolbox for everyone to use.
And this is super important. The Meta team didn't just build this one giant, inaccessible model and call it a day. No, they took all that knowledge and distilled it down into a whole family of smaller, way more efficient models. This is what makes its power actually usable for real-world, everyday stuff. And just to show you how general purpose this thing is, its power goes way beyond your typical photos. They threw it at a totally different problem, analyzing satellite images. And it actually beat out specialized models that were custom-built just for that job. We're talking about things like mapping the height of a forest canopy from space with insane accuracy. That's versatility. When you put it all together, what you're looking at is a major step towards what you could call the holy grail of AI vision research. A single universal model that learns how to see by itself and can then be pointed at almost any visual problem you can think of. And that kind of leaves us with this one big, fascinating question to chew on. If an AI can really learn to see the world on its own terms, finding patterns in billions of images that we'd never notice, what is it going to show us? What new things will it help us see that we've been missing all along because of our own human way of looking at the world?